Okay, we're starting the chapter on axioms of probability, and this really follows up on the theories of probability chapter, but we're going to use some tools that we picked up in the last couple of chapters about sets in particular and logic to some extent. I'm not sure I'm going to be able to cover the whole thing today, so some of it may bleed over into Thursday. In fact, that's kind of what I expect. We'll see how things go, but it's possible that I'll postpone the next problem set. Right. So we've talked about what probability is supposed to mean, or a number of different competing theories for interpreting what it means to say, for the sake of argument, that the chance that a fair coin lands heads when you toss it is 50%. We're now going to set aside, for the moment, the issues of what probability means and talk about mathematical properties of probability that are common to, that are sort of required for something to be called a probability, separate from the interpretation. This is the math. So the next little bit is going to be math stuff. The interpretation of it will hark back to the theories of probability that came earlier. So probability satisfies something. For some function to be called a probability, it has to satisfy three axioms. So probability, mathematical probability, is a function that assigns numbers to sets. Okay, it's a function p, and implicit we have some outcome space S, some set of things that could possibly happen, and a probability p is a way of assigning numbers to subsets of S, and it has to satisfy three conditions to be called a probability. First of all, the probability of any subset of S has to be non-negative. There's no such thing as a negative probability. So, right, P assigns a number to the subset A of the outcome space S. And the number that it assigns to any outcome whatsoever, any event whatsoever, has to be non-negative. Second thing is that the P of the entire outcome space, probability of S, has to be 100%. That is, it's certain that something is going to happen. If the probability of something is 100% or 1, it's said to be sure or certain. Doesn't mean it has to happen, just means the probability that it happens is 1. Okay, so I mean, an example of this is, we talked about tossing a coin, and it could happen that the coin never lands, right? It's a possibility that a bird swallows the coin, or the coin dematerializes and rematerializes in the center of the sun, or something like that, right? But the probability of that is 0. So the probability that the coin lands is 100%. It's certain that the coin is going to land, even though it's possible that it might not land. Okay, and then the third axiom of probability is that if I have two events that are disjoint, the intersection of those events is empty, then the chance that either of them occurs is the sum of the chances that they each occur. Okay, so if A and B are disjoint, then the chance of the union of A and B, the probability of the union of A and B, is the probability of A plus the probability of B. Okay. Pretty much everything we're going to talk about probability mathematically follows from those definitions, those axioms, and then in addition to the axioms, there are going to be a few definitions, like the definition of conditional probability. Now, this only considers pairs of events, and from pairs you can build up finite sequences, but there's an axiom that's sometimes substituted for axiom 3, this axiom 3 prime, which basically says that if we have a partition of some event A, then the probability of A is the sum of the probabilities of the sets that partition A. Remember what a partition is? It means that every pair of these is disjoint, and the union of them is equal to A. Okay, so everything that's in A is in exactly one of these sets. Okay? Sort of like taking a big set and carving it up into disjoint pieces. Okay, so this is sometimes used. For us, this distinction isn't really going to matter, but that this is just technical stuff. All right, so what are some examples of things that satisfy the axioms of probability? Perhaps the simplest example of a probability distribution is the uniform probability distribution. And what it does is it basically says if I have an outcome space S, let's say that S is the numbers 1, 2, 3 on up to n, then the probability of any subset of S is equal to the number of elements that are in that subset. So this hash mark is pronounced cardinality. And what it's defined to be is the number of elements in a set. So the cardinality of a set A is the number of elements in a set A, if A is finite. If you have transfinite numbers, then cardinality gets more complicated. You have things like Aleph null and the power of the continuum and things like that. We're not going to worry about that. OK, so this hash mark means the number of elements in the set. And the uniform probability distribution on a finite set is defined so that the probability of any subset of the outcome space is equal to the number of elements in the outcome space divided by the total number of elements in the set. So the chance of a set A is the number of elements in A divided by the total number of elements there are in S. Okay? So an example, so first let's verify that this satisfies the axioms, that you really can call it a probability. So in order to be able to call it a probability, it has to satisfy those three axioms. First of all, is it possible that this P defined this way could assign a negative number to some subset? The answer is no, because no set has a negative number of elements. And so the number of elements in a set is always at least 0. So the probability of a subset is always at least 0 divided by n, which is 0. So you can never get a negative probability if this is how you define probability. What's the second axiom? It's that the chance of S, the probability of S, has to be 100%. So if we define probability this way, the uniform probability, what is the chance of S? Well, it's the number of elements in S divided by the number of elements in S, which is 100%. So it satisfies the second axiom. What about the third axiom? Well, that says that if A and B are disjoint, then the chance of A or B has to be the chance of A plus the chance of B. Well, if A and B are disjoint, the number of elements in the union of A and B is the number of elements in A plus the number of elements in B. They don't have any elements in common, right? So since the number of elements in the union is the number in A plus the number in B, then the chance of the union is the number of elements in the union divided by total number of things there are. That's the number in A plus the number in B divided by that. That's the number in A divided by that plus the number in B divided by that, right? So it works out. So this is an example of something that satisfies the axioms of probability. It can be called a probability. And it's probably the simplest thing. We're going to use the uniform probability distribution really often to model things like dice rolls, coin tosses, shuffling a deck of cards. If we're talking about a well-shuffled deck of cards, what are we talking about a uniform distribution on? What would have the uniform distribution? Let's back up. We're talking about rolling one die, one fair die. What would we represent as having a uniform distribution? We're rolling a die, and the thing we're interested in is how many spots are showing on the top face of the die. I feel all alone up here. Okay, so what are the possible outcomes if I roll a die? What are the possible outcomes for the number of spots that show on the top face? 1 through 6. And so uniform probability distribution would say that the chance that I roll a 1, for the sake of argument, is equal to the number of elements of the set 1 divided by the, so what's the total set of things that could possibly happen? What's the outcome space for the number of spots that show on top of a die when you roll a die? Okay, so the outcome space S looks like 1, 2, 3, 4, 5, 6, right? Those are the things that could possibly happen, the numbers that could possibly show on the top face, okay? And so what's the uniform distribution on this? Okay, so what is a probability going to do? It's going to assign numbers to subsets, right? In such a way that the chance of a subset is equal to the number of elements in the subset divided by the total number of elements. So what's the total number of elements in S is equal to what? 6. Okay, so the uniform probability distribution says that the probability of a set A is equal to the number of elements in A divided by 6. So in particular, it would say that the probability that I get a 1 on the top face is equal to the number of elements in the set 1 divided by 6, which is 1/6, right? What's the probability that I roll an even number? Okay, so what outcome corresponds to rolling an even number? Okay, so 2, 4, 6. That's the event that I roll an even number, right? So the probability of 2, 4, 6 is equal to the number of elements in that set divided by 6, which is 3/6. Right? Okay, so this is what we're talking about. Okay, the uniform distribution in this case says the probability of a particular event is the number, is the cardinality of that event, the number of outcomes there are in that event, divided by the cardinality of the whole outcome space. Okay? All right, what about rolling a pair of dice? And I'm interested in the number of spots that show on top of the 2 dice. Let me say that slightly separately. I'm going to roll a red die and a blue die, and I'm interested in the number of spots that show on each of them. What does my outcome space look like? Sorry? No, I'm not the sum of the numbers that show, but the numbers that show on each face. So we have 2 dice. Okay, so I have pairs of, my outcomes are comprised of pairs of numbers, right? How many numbers show on the first die? How many numbers show, how many spots show on the first die? How many spots show on the second die? Yes? Okay, so my outcome space looks like 1, 1, 1, 2, 1, 3, etc. 1, 6, 2, 1, 2, 2, on up to 2, 6, etc. on up to 6, 1, up to 6, 6. Okay? So how many things are there in this set? So this would be S. Six times 6, right? There's 6 choices for the number of spots on the first die, 6 for the number that show on the second. Fundamental rule of counting says the total number of possibilities is 6 times 6, because knowing that, no matter what I get on the first die, I still have 6 choices for what happens on the second. Yep. So the number of elements in S, cardinality of S, is equal to 36. Okay. And so what's the event that I roll a 7? That the sum of the spots on the 2 dice is equal to 7? Yeah, just saying the sum of the spots showing on the 2 dice is 7. What does that look like? Okay, so it's a subset of the outcome space, right? Okay. What does that subset consist of? 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Okay. 1, 2, 3, 4, 5, 6 elements, right? Okay, so for the uniform distribution, on pairs of rolls, what's the probability that I roll a 7? So it's the number of elements in that set divided by 36, which is 6 over 36, which is 1/6. Okay? Is this everybody with me? Okay.
Does uniform distribution between the probability? Is that what you're asking when you say that? Or?
Well, I mean, if the dice were weighted, then these wouldn't have a uniform distribution. You wouldn't have a uniform distribution on these pairs. If the dice are fair, that's kind of what we mean, that every one of these outcomes is equally likely. This is sort of tied to the theory of equally likely outcomes. We're saying that, according to the uniform distribution, the elementary outcomes are equally likely. And as a result, the probability of some event is equal to the number of outcomes in that event, the number of elementary outcomes in that event, divided by the total number of elementary outcomes. So in this case, the probability of that I get any of these 6 disjoint things is equal to a 36 plus a 36 plus a 36 plus a 36, et cetera. Okay. Now, when I shuffle a deck of cards well, what are the possible outcomes of that shuffling? What does the shuffling procedure do? It orders the deck. It puts the deck in some order. So the outcomes of shuffling the deck are orders of the 52 cards in the deck. Okay? One possible outcome would be ace of spades, 2 of spades, 3 of spades, etc., on up to king of spades, ace of hearts, 2 of hearts, etc., on up to king of hearts, etc. You know, so the 52 cards laid out in that order. That's one possible outcome. All right. Another possible outcome would start with the 2, right, and go all the way up, and then have the ace of spades at the end. So how many different possible outcomes are there? 52 factorial. Okay. So for shuffling a deck of cards, the number of outcomes of the shuffle, if you like, is 52 factorial. Okay, and so what would be, for the sake of argument, the probability that that the first card is the king of spades, the top card? For the uniform distribution on shuffling. Okay, well, I need to figure out how many outcomes there are for which the king of spades is the first card, is the top card after shuffling, and then divide that by 52 factorial. So how many outcomes are there where the king of spades is first? Well, I could have the king of spades first and then the 2 of diamonds second. I could have the king of spades first and then the 3 of clubs second. And then there's a whole bunch of outcomes of shuffling that have the king. If it were only one out of 52 factorial that had the king of spades first, the probability of the king of spades first would be microscopic, right?
So 51 factorial over 52.
51 factorial, I have conjectured. Okay, how do we think this through? Well, we need the king of spades to be first. Okay. And then for the king of spades first, what choices do I have for the rest? I have 51 choices for what comes second, 50 for what comes third, etc., on up to 1 for what comes 52nd. Okay? So exactly right. It's 51. There are 51 factorial orderings of the deck that have the king of spades as the top card, or the first card. So this is equal to, therefore, 51 factorial over 52 factorial. And that looks an awful lot like 1 over 52.
That's the same way we were thinking about it before, where we said there's only one king of spades, so there's only one outcome, so it's one. Oh, never mind. Never mind. Yeah.
It's not that there are 52 factorial outcomes. We're only getting 1 out of 52. Okay? So it makes sense that there's, having put the king of spades first, there's a whole lot of ways you can arrange the rest of the cards, right? Many, 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 many. Yep. In fact, 51 factorial many. Okay. Okay, so our model for a well-shuffled deck is going to be that those 52 factorial orderings of the deck are equally likely. That is, uniform distribution on the 52 factorial possible orderings. This is actually going to be very, this is a different probability distribution that we're going to use a lot. It's the probability distribution for a single trial. So I'm going to do, yes,
I have a quick question.
please.
So if you wanted to read for the top card for any card, let's say like ace of hearts, it would be the same thing?
Right, so the probability that the ace of hearts is the top card is also going to be this. Okay, what's the probability that the top card is king of spades or ace of hearts? How do we do that? Well, we need to know how many ways there are that the top card can be either the king of spades or the ace of hearts, and then divide that by 52 factorial, right? Okay, if the top card is the king of spades, is the top card the ace of hearts? No. No. And if the top card is the ace of hearts, it's not the king of spades, right? So these are disjoint. So the probability, by the third axiom, the probability that either this happens or this happens is the sum of their probabilities, right? Okay, each of them have probability 1 over 52. So what's the probability that either of them happens? Right, it's 1 over 52 plus 1 over 52. Sorry?
2 over 52?
Yeah, 2 over 52, yeah. I'm sorry, did I? Right, so because the events are disjoint, by the third axiom, the probability of their union is the sum of their probabilities. Right? This is the union of two events. It's the event that the top card is the king of spades, union, the event that the top card is the ace of hearts. Those two events are mutually exclusive. They're disjoint. So the probability of their union is the sum of their probabilities by the third axiom. The probability the top card is the king of spades is 1 over 52. The probability the top card is the ace of hearts is 1 over 52. So the probability of either of these things is 2 over 52.
How about when we're talking about the second card?
Same thing. Probably the second card is the king of spades is 1 out of 52. How do we do that? Well, if you want to think about the orderings of the deck, I'm going to say that the second card is the king of spades. There's one card in front of it, and then there's 50 cards behind it. So having put the king of spades here, how many choices do I have for what comes first? 51, and then I've got 50, 49, etc., on down to 1. So there's still 51 factorial orderings of the deck that have the king of spades as the second card. There's 52 factorial orderings of the deck in all. So the probability that the second card is the king of spades is 51 factorial over 52 factorial, which is 1 over 52. Okay? The same as before. Let's do this and then come back to cards again momentarily. So we're thinking now about a single trial like tossing a coin, and we're going to label the outcomes, the possible outcomes as being 0 or 1. So we'll say that if the coin lands heads, we'll call that 1. If the coin lands tails, we'll call that 0. Or if the coin lands heads, we'll call it success. If the coin lands tails, we'll call it failure. We have two possible outcomes. It's a single trial that can result in two possible things happening. And we're going to define the probability distribution as follows. The chance that of a 1, chance we get heads, is p. The chance we get 0 is 1 minus p. The chance of anything, the chance of heads or tails, is 100%. And the chance that we don't get anything at all, the coin doesn't land, is 0. Okay? Now, this satisfies the axioms of probability, right? P is some number between 0 and 100%. So if p is between 0 and 100%, so is 1 minus p. Right? Okay? So there are only, how many subsets are there of, the outcome space here, S, is equal to 0, 1. Those are the only possible things that can happen. This set has two elements. How many subsets can you make from a set with two elements? If we have a set with n elements, how many subsets can we make from a set of n elements? For each element, we get to decide whether that element is going to be in the subset or not, right? Okay, so there's two possibilities for whether 0 is in the subset. Having put 0 in the subset or not, there's two possibilities for whether 1 is in the subset. Okay, so there's 2 times 2 squared possibilities. Remember when we were talking about the binomial coefficient, combinatorics, we talked about the number of possible subsets of a set with n elements is 2 to the n. Because you have a tree, you get to decide, is the first element in the set, yes, no. If it is the second element in, yes, no, et cetera. And so you end up getting 2 to the n possible elements. So if we have a set with 2 elements, there are 2 to the 2 equals 4 possible subsets. What are they? Well, we can have none of the elements in the subset. We can have one element in the subset. That can happen 2 different ways. Or we can have both elements in the subset. Those are the 4 subsets of this set. Okay? And there are no others. That's it. Right? Okay. So if we want to verify that this distribution, this way of assigning a number to a subset really is a probability distribution, we need to verify that it satisfies the axioms. So does it assign a non-negative number to each one of these things? Yeah, it assigns 0 to that, 1 minus p to that, and 1 to that. All those numbers are positive. Okay? It assigns 1 to that. That's the second axiom. And what's the third axiom? Well, that the chance of the union of any two of these things is the sum of their chances if they're disjoint. Okay, so what are the disjoint possibilities here? Well, that and that are disjoint, because the empty set is disjoint from everything. So what's the chance of the union of that and that? Well, the union of the empty set in any set is just the original set. So the chance of this or this is the chance of this, which is 1, which is 0 plus 1. So it satisfies that. Okay? Similarly, the chance of this union any of these is going to be 0 plus the probability of that. It's going to work out. And the only complicated case is this one, where we look at the chance of this union that. Okay? Well, what is the chance of that union that? That union that is this. Yes? The chance of this is 100%. The chance of that is p. The chance of that is 1 minus p. P plus 1 minus p is 1, 100%. So it works out. It satisfies the third axiom as well. So this really is a probability distribution. Okay. Everybody's glazed. All right. So, probability that you get 0 or 1, right? This, what is 0 or 1? It's this. Okay? And what is the probability of 0, 1? Well, it's defined to be 1. Okay? So, and that's in fact probability of 0 plus the probability of 1. because that's P and that's 1 minus P. They sum to 1. Okay. There are some rules that follow from the axioms. They are not themselves axioms. They're consequences of the axioms. They're true. They have to be true. They're always true. They're true as math facts that you can derive from the axioms, but they are not themselves axioms. They're consequences. Now, one of those consequences is that the chance of the complement of an event is 100% minus the chance of the event. Okay, so I claim that you can derive that from the axioms. How do you do that? Well, we can write, if for any set A whatsoever, the outcome space is A union the complement of A, right? Something is either in A or it isn't in A. Those are the only possibilities. Okay? So A union A complement is S. Moreover, A intersect A complement is empty, right? Nothing can be both in A and not in A at the same time. Yes? So according to the third axiom, the chance of A union A complement is the chance of A plus the chance of A complement. Right? But A union A complement is S. The chance of A union A complement is the chance of S. That's 100%. But because A and A complement are disjoint, the chance of A union A complement is the chance of A plus the chance of A complement. So what do we have? The chance of A plus the chance of A complement is 100%. Just subtract P of A from both sides, you get the chance of A complement. For convenience, often, that if we want to calculate the chance of an event, it can often be much, much, much simpler to calculate the chance of the complement of the event and then subtract that from 1, rather than to calculate the chance of the original event. This is typically the case if we're looking at the probability of at least 1 or not all or something like that. So the example that's in the text is, suppose I toss, let's look at what we just did for the deck of cards. What's the chance that the top card is not the king of hearts? Well-shuffled deck, 52 factorial possible orderings, uniform distribution on those orderings. What's the chance the top card isn't the king of hearts? All right, using the complement rule, right? Chance top card not the king of hearts is 1 minus the chance the top card is king of hearts. Right? Okay. What if we wanted to do it from scratch? Well, what's the chance the top card isn't the king of hearts? Well, we could divide that up and say, okay, that's the chance the top card is the ace of spades, or the 2 of spades, or the 3 of spades, or the 4 of spades, or blah, 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 right? There are 51 possibilities that are not the king of hearts. Those 51 possibilities are mutually exclusive, because if the top card is the ace of spades, the top card is not the 2 of spades, right? So we could add the chances of each of those possibilities to find the chance of their union, the chance that the top card is anything but the king of spades. Each of those things, what's the chance the top card is the ace of spades? Did I say, I meant king of hearts. I think I said king of spades. What's the chance that the top card is the ace of spades? Okay. A few minutes ago, we agreed that the chance the top card is any particular card is 1 out of 52. Right? Okay, so chance that it's the ace of spades is 1 out of 52. Chances the 2 of spades is 1 out of 52. Chances the 3 of spades is 1 out of 52. Right? We add up all of those possibilities, but not the king of spades. So we get 1 out of 52 plus 1 out of 52 plus 1 out of 52, 51 times. So that would give us 51 over 52. This is easier. Okay. All right, so complement rule can definitely help. What is the probability of the union of two events that aren't necessarily disjoint? So the axioms tell us that if we have two events that are disjoint, the probability of their union is the sum of their probabilities. But if we have two events that aren't disjoint, what's the probability of their union? Well, the way we can figure this out is by partitioning their union. And this is easiest to see with a picture. Okay, so A union B is that, right? Okay, we're going to divide A union B into, we're going to partition it into three subsets. Okay? One of the subsets is going to be the stuff that's in A but not in B. So how do I write that in symbols? What's stuff that's in A but not in B? Okay. A minus the, so we don't really have a notion for subtracting sets yet. There is such a notion, we don't have that. It is in A and not in B, right? A, B complement. That's stuff that's in A and not in B, right? Okay, so that's, if you like, that's this stuff, right? That's A intersect B complement. Okay. Then what's this stuff over here? Okay. So I'm going to write it A complement B, but it's the same thing. And then what's that stuff? AB. Right, A intersect B. All right. Are these mutually exclusive? Are these disjoint? Yeah, okay. Suppose I'm in AB complement. Then I'm not in B. Both of these, to be in either of these, I have to be in B. Okay, so if I'm in this, I'm not in either of those. Right? Suppose I'm in this one. If I'm in this one, I'm not in A. If I'm not in A, I can't be in that or that because those require me to be in A. Right? Okay, so these three are mutually exclusive. If I'm in this one, I have to be in both A and B. In this one, I'm not in B, and in this one, I'm not in A. Right? So I can't simultaneously be in any pair of these things. There's no way for a dart to stick simultaneously in any two or more of these three sets. If I thought of this as a dartboard, it can only stick in one. Okay, so by the third axiom, the chance of A union B is the chance of this plus the chance of this plus the chance of this because these three are disjoint. Okay? It's like area. If I thought of these things as the area of a subset of this rectangle S, the area of this union is the area of this piece plus the area of this piece plus the area of this piece. They don't overlap. Okay? So the probability of A union B is the probability of this plus the probability of this plus the probability of this. So far, so good? Okay. Now, what happens if I take P of A plus P of B? I hate dividing the work across the screen, but what's P of A plus P of B in terms of the pieces that we've got over here? Well, I can write A as the union of this piece and this piece, right? It's the stuff that's in A but not in B, union the stuff that's in both A and B. So A is this piece, union this piece. Similarly, B is this piece, union this piece. Okay? So I can write A, that's the probability of A, B complement union AB, plus the probability of A complement B union AB. Right? Because that's just another fancy way of writing A. That's a fancy way of writing B. But this and this are disjoint. And this are disjoint. So the probability of this union is the probability of that plus the probability of that. And similarly, probability of this union is probability of that plus the probability of that. So what is this? This is P of A, B complement plus P of AB plus P of A complement B plus P of AB, which is P of AB complement plus P of A complement B plus 2 probability of AB. Right? If I take the area of this plus the area of this, I've counted the area of the intersection twice. So the area of the union, I got to subtract off one of those intersections because I counted it twice. So this thing, this sum, is the same as that, except this only counts the intersection once. Right? So what we've just shown is that, somewhere here in the missing board space, for any two sets whatsoever, probability of A union B is probability of A plus probability of B minus probability of the intersection A and AB. Okay? In the special case that A and B are disjoint, A intersect B is empty. The probability of the empty set is 0. So in the special case that A and B are disjoint, this reduces to the third axiom. When A and B are not disjoint, we get this extra thing to subtract. Now, I just said that the probability of the empty set is 0, and that's actually a result which we haven't proved, but it follows from the complement rule. Right? Complement rule says probability of A complement is 1 minus the probability of A. So what's the probability of S complement is 1 minus the probability of S, which is 1 minus 1, which is 0. What's S complement? The empty set. Okay, so the probability of the empty set is 0, probability of S is 1. All right. Now, are there any sets for which the probability of A intersect B is negative? No. By the first axiom, whatever I plug in over here, this piece that I'm subtracting is positive, right? So we have an inequality that says that no matter what A and B are, probability of A union B is less than or equal to the probability of A plus the probability of B. Okay. Can I put something over here to the left of this? Do I know something that can't be any bigger than the probability of A union B? This is also less than or equal to 1. Sorry? P of the empty set. Okay, so somewhere way over here, I've got 0. Okay, let's draw a Venn diagram. Let's grab an eraser. All right. This is A intersect B. That's A union B. Can the probability of A is the probability of A intersect B complement plus the probability of A intersect B, right? So to get the probability of A, I'm going to add something to the probability of A intersect B. Namely, I'm going to add the probability of A intersect B complement. A intersect B complement, its probability can't be negative. Right? So the probability of A has to be at least as big as the probability of A intersect B. Similarly, the probability of B has to be at least as big as the probability of A intersect B, because I'm taking A intersect B, union some disjoint piece. The probability of that piece can't be negative. I've got to be adding something. Well, I can't be taking anything away. So I know that the intersection of the two things is only part of the union. Yes? So this has to be less than or equal to the probability of A intersect B. Right? Probability of the intersection is going to be less than the probability of the union. Probability of the intersection is also less than the probability of A, right? Because it's only a piece of A. Probability of the intersection is less than the probability of B because it's only a piece of B. Yes? Okay, so this is less than or equal to, for the sake of argument, probability of A. It's also less than or equal to probability of B. I don't know whether probability of A or probability of B is bigger. But this is true with A there. It's also true with B there. Yes?
But isn't P of A union B is exactly equal to PA plus PB?
Only if they're disjoint. The question was, isn't probability of A union B equal to the probability of A plus the probability of A? It's like, no, it's equal to this. If they're disjoint, this is 0. If they're not disjoint, I need to subtract something off. Because I've counted their intersection twice. Okay. All right, so this lets us find bounds on probabilities without knowing a whole lot else. So let's look at an example of that. Okay, so we have two events A and B. Chance of A is 95%. Chance of B is 83%. What's the chance of A union B? What do we know about it? Is it 100%? No. Okay, in particular, the Venn diagram might look like A could be here, and B could be a subset of it, right? So the chance of their union could be just the chance of A, right? But learn the trick that you guys taught me the other day. Okay, so that's not true. Is it at most 100%? Yeah, chance of anything is at most 100%. Okay, it's got to be at least 95% because when you take A and include B as well, you're certainly not taking anything away from A, right? So the chance of the union is A plus B minus the intersection. If B is already there, then, okay. So it's at least 95%. If it's at least 95%, it is at least 83%, right? That makes sense to everybody? Okay. This is, again, where people will get confused because they will think that if it's at least 95, then they don't need to answer this. But they're both true, so you have to answer them both. They have to be true, right? Okay. All right, we deal 5 cards from a well-shuffled deck. A is the event the first card's an ace. B is the event the second card is an ace. What's the chance of the union? First of all, in words, what is the union? First card is an ace, or the second card is an ace, and then implicitly, or both, right? It's not saying that they don't both happen. It's either or both. Okay, so how do we, okay, what are the possible answers here? So is it the chance of A plus the chance of B? Are they disjoint? Can the first card be an ace and the second card be an ace? Yes. Okay, so the chance of their union is not the sum of their chances because they're not disjoint. Right? The chance of their union is the sum of their chances minus the chance of their intersection. Right? They do have an intersection. Right? They're not disjoint. That intersection has positive probability. It's the chance that both the first and second cards are aces. So this piece I'm subtracting is a positive piece, right? So the chance that either A or B happens isn't as big as the chance of A plus the chance of B. It's less than that. So this is it, right? Okay.
I don't get the first part, the less than a chance A occurs. What do you mean by less than a chance A?
The chance that you get either an ace as the first card or an ace as the second card is less than the chance that you get an ace on the first card plus the chance you get an ace on the second card. Right? It's exactly this. Chance of A union B is less than or equal to the chance of A plus chance of B. In this case, it's strictly less than because the chance of the intersection is positive. Okay. 2 events. A and B. Chance of A is 18%, chance of B is 49%, chance of the intersection of A and B is 18%. What do we know? The chance of the intersection is the chance of A. How can that happen? A has to be a subset of B, right? Because when we take the intersection, we're not losing anything. Okay. So if A is a subset of B, what does that mean for implication? Something, it means something implies something. Okay. Sorry, A is the smaller one. Okay. Right? We've got this situation. Can a dart stick in B without sticking in A? Yes. Can a dart stick in A without sticking in B? No. Okay. A implies B. If A happens, B happened also. Okay. Let's see. Get into conditioning. I think that's, yeah. Okay. All right. Let's do one more here. We've got, let's do this 14.5. We have 3 events, A, B, and C. Chance of A is 23%, chance of B is 25%, chance of C is 37%. What can we say about the union, the probability of the union, A, union B, union C? Is it at least 23%? Yeah. Okay. Okay. Can it be bigger than 37%? Yeah, because if any part of A or B is not already contained in C, you'll be increasing the probability of the union when you include them, right? So it can be bigger than 37. Is it at least 25%? Yeah. Is it at least 37%? Yes. Is it 23 plus 25 plus 37. Not necessarily. It would be if you knew they were disjoint, right? But you don't know they're disjoint. So that's it. Yep. It would be, so if I've done the math right, 50, 60, 85. Yeah, it's at most 85%. Yeah. All right. Okay, we're going to start. Yes?
So how do you know A and B are not subsets of C?
They might be. I don't know that A and B are not subsets of C. Okay, so this is true. We're trying to select the statements that are true regardless of the relationship between A, B, and C. So it's true. This is what we selected is true even if A is a subset of B is a subset of C. It's true if A is a subset of B and then B and C are disjoint. It's true for any relationship between them. Those things have to be true. Okay. All right. We're about to get a new definition called conditioning, conditional probability. And this describes a situation where you learn something about what happened. So, for example, let's say that I toss a coin 3 times. Let's see how hard we get this example to be. All right, and we're going to assume that everything is nice and clean and fair, and so we have a uniform probability distribution on what? What are our outcomes that we have a uniform probability distribution on? What are the outcomes? Each toss can give me a head or a tail. 3 tosses gives me a sequence of length 3, comprised of heads and or tails, right? So it's uniform distribution on this set of things that look like this. Heads, 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 tails, heads, tails, heads, tails, heads, heads. How many are there in all? Should we write them all down? No? Okay, there's 8 in all, right? Because I have 2 choices. There's 2 possibilities for what the first toss gives me, 2 possibilities for what the second toss gives me, no matter what the first toss gave me, and 2 possibilities for what the third toss gave me, no matter what the first and second did. So 2 times 2 times 2 is 8. So far, so good? Okay. So what is the probability that I get 3 heads? What is the subset of outcome space that corresponds to getting 3 heads? There's just one element there, right? I have to get heads on all 3 tosses. So that's heads, 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 which is 1 over 8. There's only one elementary outcome there. There's only one element in that subset. Okay, and there's 8 elements in all. They're equally likely. We're using uniform distribution. That's kind of what we mean by a fair coin. Okay, so now suppose that somebody tells me that the first toss gave me a head. What's the probability that I get 3 heads in the 3 tosses in all? All right, so I've learned something new. It's learning in this sense of the way you sort of update a probability to account for new information is called conditioning. So what we want to find is what's the conditional probability of getting 3 heads given that the first toss gives you a head. Okay, so 1/4 is what people are saying, and I agree. And now we just want to make it formal. Okay, so probability of 3 heads given, so use a vertical bar to denote given. First toss gives a head is equal to 1/4. What are we doing? We're basically saying, well, I know that the outcome is one of the outcomes that has heads as the result of the first toss. Yes? So how many of those are there in all? 4. Yes? Let's write down what those are. Heads, heads, heads. That's the one I care about. Heads, tails, heads. Heads, heads, tails. Heads, tails, tails. Right? Okay. I know that this happened. The outcomes in here are still equally likely. In one of these 4, I got all three tosses were heads. And so the conditional probability of 3 heads, given that the first toss gave me a head, is 1/4 instead of 1/8. All right. This is kind of heuristic. There's actually a definition going on here. Right? We've kind of got an intuitive feel for what's happening, but there's really a definition, and the definition is this, that the conditional probability of an event A given B is equal to the probability of the intersection divided by the probability of B if the probability of B is positive. Right? We don't divide by 0. All right. That's what we just did. The probability of 3 heads given head on the first toss is the probability of 3 heads and heads on the first toss. That's 1/8, right? To get 3 heads, we had to have a head on the first toss. So in this case, this is 1/8 divided by, what was the probability of a head on the first toss? It's those 4 outcomes out of the 8 possible outcomes. So it's 1/8 divided by 1/2, which is 1/4. So that's what we just calculated. But we were kind of, intuiting our way through it rather than doing something rigorous. In fact, this is the definition. So I use 3 bars indicating that this is a definition. In this particular case, it reduces to this. Okay? So that's conditional probability of A given B. And it's used to describe learning something. Yes?
What's the line mean? Because
Given. No, it's not. So if these were logical propositions, then this would be or. But this is conditional probability. So we're going to have different context. The vertical bar here is pronounced given. And it's defined exactly this way. What's the chance of A given that B occurred? We good so far? All right, so what's the chance that the first, we shuffle a deck of cards well. What's the chance that the top card is the King of Hearts, given that the second card is the King of Spades? Okay, just from the definition, this is probability that the top card is King of Hearts and the second card is king of spades, divided by the probability that the second card is king of spades. Right? You shuffle a deck of cards. Somebody shows you that the second card is a king of spades. How are you going to bet on whether the top card is a king of hearts? Right? What odds would be reasonable to take? What's the chance the top card is the king of hearts and the second card is the king of spades? We have the uniform distribution on orderings of the deck, right? All 52 factorial orderings are equally likely. They'll have probability 1 over 52 factorial. How many of those give us the first card, king of hearts, second card, king of spades? We got no choice for what comes first, no choice for what comes second, 50 choices for what comes third, 49 for what comes fourth, etc. Right? Okay, so there are 50 factorial orderings that give us the top card, the king of hearts, and the second card, king of spades. The probability is therefore, of this numerator probability is therefore 50 factorial divided by 52 factorial. Right? So the numerator, we've got 50 factorial over 52 factorial. What's the denominator? Okay, second card, king of spades. We have 51 choices for the first card, 50 for the third card, 49 for the fourth card, etc. So we've specified one of them. There's 51 factorial different orderings of the deck that have the king of spades as the second card. So the probability that the second card is the king of spades is, as we found before, 51 factorial over 52 factorial. Right? These cancel. That gives us 50 factorial over 51 factorial, which is 1 over 51. All right, does this kind of make sense intuitively? Somebody tells you what one of the cards in the deck is in a different place from the one you care about. There's 51 different possibilities left for what was first. They're all equally likely. 1 over 51 chance that that first card was the king of hearts. That make sense? All right. You've ruled out one of the possibilities, the king of spades. So far, so good? Okay. It turns out that conditional probability behaves just like probability does. So, for example, we've basically, in conditioning on the event B, learning that B happened for sure, what have we done? We've changed the outcome space from being all of S to just being B. We know that B happened. We know that whatever happened was in B. Okay? So the chance of A given B is greater than or equal to 0, just like the chance of A. The unconditional chance of A is greater than or equal to 0. The chance of B given B is 100%, just like the chance of S is 100%. But once you know that B happened, you know that B happened. The chance of the union of two things given B is the sum of their chances given B, provided they are disjoint. Okay? Chance of A complement given B is 100% minus the chance of A given B. All the usual sorts of things follow through for conditional probability as well. All right, here is a notion that for some reason confuses. But let's beat on it for a little while and we'll see what happens. All right, independence. The heuristic behind independence. Independence is a relationship between events. Two events are independent if learning that one of them happened doesn't tell you anything about whether the other happened. They're uninformative with respect to each other. Okay? So if I toss a coin twice in a fair way, the event that the first toss gives me heads is independent of the event that the second toss gives me heads. knowing that I got heads on the first toss doesn't tell me anything at all about whether I got heads on the second toss. Does that make sense? It's uninformative. Right? It's different from being disjoint. Right? They're not disjoint. I could get heads on both tosses. You get heads on the first and on the second. Right? The heuristic for independence is knowing that one event happened doesn't tell you anything about whether the other did. The mathematical definition is, so how do you say learning that one happened doesn't tell you anything? How do you make that math? Well, you're saying the conditional probability of one event given the other is just what the original probability was of the first event. It doesn't, you didn't learn anything by learning that the second event happened. You didn't learn anything about the first. So probability of A given B is just the probability of A. Learning that B happened doesn't tell you anything about whether A happened. It doesn't change the probability. Similarly, probability of B given A is just the probability of B. Learning that A happened doesn't tell you anything about whether B happened. Now, the definition of conditional probability involves dividing by something that in some circumstances might be 0. And so we have to rule out the possibility that P of B is 0. We can come up with a definition of independence that doesn't require this by just saying we define two events to be independent if the chance of their intersection is the product of their probabilities. Now, that's equivalent to this unless P of A or P of B is 0. If P of A or P of B is 0, this definition still makes sense, but a definition in terms of conditional probability doesn't. So let's just do the math. Let's suppose that P of B isn't 0. So P of A given B is P of A intersect B over P of B, right? And we are saying that that is in fact equal to P of A if the events are independent, right? If the events are independent, learning that B happened doesn't tell me anything about whether A happened, so this conditional probability should be equal to this unconditional probability. That's our stopgap definition before we do something more general. Well, if that's true, I can multiply both sides by P of B, and that says that P of AB is P of A times P of B. Okay? This expression only makes sense if P of B is not 0. This expression always makes sense whether P of B is 0 or not. So we take this to be the definition because it's a little bit more general. Okay. If this holds, that holds, as long as you're allowed to divide by P of B. We all together? You guys are holding up very well considering we didn't take a break today. All right, let's suppose that A and B, let's suppose that P of A is bigger than 0 and P of B is bigger than 0, and that A and B are mutually exclusive. Okay, so P of A is bigger than 0, P of B is bigger than 0, and A and B are mutually exclusive. Can A and B be independent? No. Right. Heuristically, if their intersection is empty, and I learn that B happened, I know that A did not happen. Right? The intersection is empty. What's the Venn diagram for that look like? Right? It's yes? If I learn that A happened, I know B didn't happen, and vice versa. If I learn that B happened, I know A didn't happen, because they don't have any elements in common. right? So if two events are mutually exclusive and neither has probability 0, they can't be independent, right? Mutual exclusivity and independence are different and, in fact, incompatible, right? So this is really, it's like you will be tempted to confuse mutually exclusive and independent. Don't. All right. Where do I want to go with this?
Could you give some examples of closing points or something?
Some examples, sorry?
Like dice or something? I don't know.
Dice? Oh, okay. So let me draw. Let me use the. Let's suppose that we are taking as a model for probability area. So we're looking at Venn diagrams, and we are saying that the probability of an event is the area of the event. The probability of the subset is the area of the subset. So here's S, here's A, here's B. We just showed that at one extreme, if A and B don't intersect at all, and let's just keep the assumption that neither of them has 0 probability for now, okay? If they don't intersect at all, they're not independent, right? They're dependent because the probability of A intersect B is 0, and that's not the probability of A times the probability of B. Because probability of A times the probability of B is some positive number because probability of A is positive and probability of B is positive. Okay, so in this situation, we've got probability of AB is less than the probability of A times the probability of B. Right? In fact, it's 0. Yep. Let's have them intersect a little bit. Okay? The probability of the intersection is going to grow. It's going to be less than this for a while. When they overlap by just the right amount, the probability of A intersect B is going to be equal to the probability of A times the probability of B. And then, as they intersect more and more, the probability of A intersect B is going to be bigger than the probability of A times the probability of B, until eventually one of them is a subset of the other. And the probability of A intersect B is just, for the sake of argument, the probability of B if B is the smaller event. So we have this range of possibilities from the probability of A intersect B being 0 on up to the probability of A intersect B being whatever the probability of the smaller event is. Somewhere in that continuum, they overlap by just the right amount to make them independent. Right, so what does that look like? Okay, so here is our Venn diagram again, and this is representing the probability of an event by its area. So A, the area of A is 30% of the area of S, and the area of B is 20% of the area of S. Right now, their intersection, their overlap is, the area of their overlap is 17.2%. What does the area of their overlap need to be for them to be independent? %20 times 30%, which is 6%, right? Okay, so I need to make them independent. I've got to find the place where they overlap by exactly 6%. So in this configuration, they're independent, right? But I'm on a continuum that ranges from probability of A intersect B being 0, if they don't overlap at all, growing, 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 until at some point they're exactly independent. And then it can grow more and more and more until the probability of their intersection is the probability of the smaller event. Okay, so independence is a very special relationship. Now I'm going to have trouble dragging them out without doing something like that, where they overlap by just the right amount. So what is that right amount? It's basically saying that the area of the intersection is to A as the area of all of B is to S. Or conversely, the area of the intersection is to B as the area of all of A is to S. Okay, so it's really, what's conditional probability? It's this area, so conditional probability of B given A is the probability of the intersection divided by the probability of A. For that to be the probability of B, that ratio, this area to this area, has to be the same as the ratio of this area to this whole thing. Okay? And similarly, probability of A given B is this area divided by that area. And for the events to be independent, that divided by that has to be the same as this divided by this. Okay? Very special relationship. Okay, I'm sorry to hold you over a minute. I'll see you guys on Thursday.